as we were saying, analysis. Oops. Engineering analysis, and we're going to have two multiple choice tests at the end of the term, and this word there might be different for the project, depending on how we're going to proceed to go about it. But you will hear more as we go along. All right. So I want to just do a little bit of discussion about the first fundamental thing that we need to do any form of analysis, because all modeling in engineering is done using differential equations. So we have to be able to know how we solve using differential equations. I know that you did a differential equations course, so anything that I'm going to say now should be very familiar to you. So let me start off with a second order differential equation. All right, so we have here a second order homogeneous equation. It's homogeneous because the output of a differential equation is equal to 0. Sorry, not the output, the input to the differential equation is 0. So because it's a homogeneous second order differential equation. So anybody can tell me the insights as to how we go about solving this?
So rewrite it, sir. Rewrite it in with the auxiliary equation.
All right. So we rewrite it with the auxiliary equation. All right. So the auxiliary equation that we're going to write down. Let me go through some first principles. Since as a maths teacher as well, I always like to make sure so we have the first principles down pat. So we'd write down the auxiliary equation, but let us just discuss where we get the auxiliary equation from. So let me digress for a little bit. Is that a trick question?
Sir, the auxiliary
4 plus what?
fine, sir.
Yeah, we're going to write down the auxiliary equation, but I'll say this is not a trick question. 4 plus what gives me 0?
-4, sir.
-4, sir.
-4. All right, sine x, and I'm going to subtract from something from it and get 0. What am I going to subtract?
Sine x, sir.
Like I say, it's not a trick question. I'm not trying to trick anybody. So if when I add or subtract the two same things, if I get 0 as my result, then all the things that are there must be the same. So I get 0 here as my homogeneous equation. So therefore, this, and this must be the same thing, must be of the same order. If only the way I get 0 is the two things have to be the same. So now I take something and differentiate it. I take it and differentiate it again, because that's dy dx and dy by dy by dt and d2y by dt squared. I get back the same thing. Now, which function you know when you differentiate it to get back the same thing?
E to the x, sir.
Yes, sir. E to the x.
So we're going to try the most general form of e to the x that we have. So we're going to write e to the kt. I'm going to differentiate it. dy by dt. When we differentiate this, like I said, I write out the most general exponential function I can find. So I put in something in front of the t and I put in something in front of the function. But when I differentiate this, what am I going to do?
K A E to the KT.
All right. So the k comes down. And when I differentiate it again, what am I going to get again?
K squared, sir.
E to the
K squared e to the kt. So I'm going to plug those back in. So therefore, I plug that back in here. I'm going to get k squared a e to the kt plus 4 k a e to the kt plus 3 a e to the kt is equal to 0. Now, if I take out the a e to the kt, what I'll be left with is k squared plus 4k plus 3 equals 0. And this quadratic equation, click on a differential equation, so I end up with a quadratic equation. This quadratic equation is what we call the auxiliary equation. But it becomes very easy to write down the auxiliary equation when we get the quadratic, when we get the differential equation. Because you see that the auxiliary equation, k squared plus 4k plus 3, and the equation that we have up here is d2y squared, d2y by dt squared plus 4 dy by dt plus y equal plus 3y equals 0. So the two things are of the same form. So we could easily look at this equation and write down our solution. So the auxiliary equation is k squared plus 4k plus 3. So we can easily look at that, look at the differential equation already. This is never 0. And so therefore multiplying these two is only k squared plus 4k plus 3 equals 0. And since me make up the equation, me can factorize it quite easily, I hope. All right, so this factorize k plus 1, k plus 3 equals 0. So therefore k is equal to -1 and -3. So therefore, I find what my y is. My y is a, call this a1, e to the k now is -1. And we have two answers. So therefore, we are going to write down our most general solution as the sum of these two answers. So therefore, I write down constant, which I'm going to call a2, e to the -3. That's the next value I find for t. So that would be my solution to my homogeneous equation. What I call most general solution. When I say most general, because e to the -t by itself is a solution. E to the -3t by itself is a solution. Multiplying by any constant at all at this point will give me a solution, will also work. When I put them together, that will also work because this will give me 0. And when I plug in, this will give me 0. So the two of them will give me 0. So this represents what my output equation is going to look like. So we are in electrical engineering. Let me just write down. When you have an inductor, L, what's the voltage current relationship? And for a capacitor, and for a resistor.
So for the inductors, LDIDT.
L di by dt. And for the capacitor, what's the voltage relationship between voltage and current? They force us to go to education class and them tell us that we must wait a little bit and we get good quality answers. So wait, all right, we'll go over here so and then come back here. So what's the voltage current relationship when you have a resistor?
Oh, no, it's IR, sir.
All right. You will find that I assume nothing in this life. I have a big lecturers at university who don't know. All right, this one here is 1 upon C, the integral of I dt. So now, let's use this in a situation where we have the three of them connected. Yep. Can't draw a straight line. All right, so the first thing, we have this problem here, and we are asked to write down the differential equation for the system when the switch is closed. So if we know Kirchhoff's law, then what can we say to write down Kirchhoff's? What do you know about the voltage across the resistor, the capacitor, and the inductor?
The algebraic sum is equal to 0, sir.
Yeah.
So the algebraic sum is equal to 0. So now we can write down, so that's the current voltage relationship, IR plus 1 upon C, integral of I dt plus L di dt equals 0. So this is going to give me 4I plus 1 over 0.2, the integral of I dt plus 5 bi dt is equal to 0 when we put in for R, for C, and for L. And that's going to be 4I plus 5 the integral of I dt plus 5 di dt equals 0. Now, one of the things that we can do is to make this equation more palatable so we can deal with it. We can differentiate everything. So we're going to take the derivative. So now, if we differentiate here, we're going to get 4 di dt. I is a function, we don't know what the function is, so we're going to have 4 di dt. When we differentiate an integral, basically we end up with the function itself. Differentiate is the opposite of integrate. So basically we have an integral and we're going to differentiate it so we cancel everything. So we're going to have that this is going to be 5i. And then we differentiate in a derivative, so that's going to give me the derivative squared. So that's going to do d2i by dt squared is equal to 0. So we can write it down. 5 d2i by dt squared plus 4 di by dt plus 5i equals 0 is the differential equation. So this is our differential equation.
Excuse me, sir. You gonna multiply 2 by 5 or something? Oh, because I was gonna ask where the 1 over 0.2 gone.
Multiply 2 by
I'm asking if you multiply 2 by 5.
1 divided by 0.2.
Okay.
Just using, so 1 divided by 0.2 is 5. So we will need to calculate. So that's how we get the 5.
Oh, I realize, sir. I realize.
Okay. So now, suppose they ask us to solve the differential equation.
We would then utilize the auxiliary equation just like before.
So then now we would write down. So the first thing we write down is the auxiliary equation. Which is going to be 5k squared plus 4k plus 5 equals 0. Now that is not such a nice equation to solve, meaning to say that can't factorize it or anything. So we will be using MATLAB a lot in the course, but this evening is just pure. We're going to use the quadratic formula. We use MATLAB, we just type in the coefficients and tell to find the roots, and it will do it. B squared is is 16 minus 4 times A is 5 and C is 5 divided by 2A. Now this leads us to another little interesting problem now. So this is going to be minus 4 plus or minus, this is 84 over 10. So now, if the roots of the auxiliary equation are negative 84, so this will lead to complex roots. I'm going to take out the 4 into 84 is 21. All right, so the square root of minus 1 is j. I would use the I in engineering because the same, it would create a problem for us. Square root of 4 is 2, and square root of 21, we're just going to leave alone. So this is going to be 2j root 21 over 10. So that is going to be minus 4 over 5 plus j root 21 over 5, 2 into the 10, 5. Now, so that would be the roots of my equation, but if it's complex, that I am told that this is Euler's, EULERS is French, and this is Euler's. You rub it down, says Euler's, don't care. That my math teacher tell me. So
I zoom out the screen a bit.
Sir, just a question. Why you never just take out the square root of negative j and just square root 84?
no, you can't do that. But I suppose it's a math teacher, isn't it? But you can't do that. Anybody know how Euler's theorem say?
I don't remember it.
Anybody remember what Euler's theorem? E to the j theta. All right, let's start off cos theta. And I'm here crickets in the background. Everybody don't know this?
You just need to remember a jog there.
Huh?
Just need to remember a jog, sir.
E to the j pi or I pi plus 1 equals 0.
That's it.
Mm. Same thing. When you say e to the I pi, you're replacing the I with the j, and the theta is now pi. But e to the j theta is cos theta plus I sin theta. Now, why I bring up that is that suppose your solution k is equal to a plus b j plus r minus. Then what your solution going to look like is y is equal to a1 e to the a plus bj t plus a2 e to the a minus bj t. Rough work we're doing here. So we're going to write y is equal to a1 e to the at, because we're going to separate these two, times e to the bj t plus a2 e to the at e to the minus bj t. So now, if we take out the e to the at, because it's common to both of them, so that's e to the at, and then we have a1 e to the bjt plus a2 e to the minus bjt. And we're going to apply Euler's theorem. So we soon come back to this problem over here. We'll just establish it. So we'll just come. So if we use Euler's theorem, we're going to have e to the at a1 cos bt plus j sin bt plus a2. We're applying Euler's theorem to this part here now. So that's going to give me cos minus bt plus j sin minus bt. Okay. Now, if you were paying attention in math class when they did the trick, most of us weren't, but some of it come back to you useful. Some of it come back to be useful. Cos minus theta is the same thing as cos theta. That's one of the things that they established in a tricks class. And sin minus theta is minus sin theta. So we're going to write, we're getting to the point of the whole entire exercise. It's a simple point, but so this now is a1 cos bt plus a1 j sin bt plus a2. Now we have cos minus bt, and what we're saying is cos of a negative number is the same thing as cos of the number. So I'm going to write a2 cos bt, because minus cos of minus bt and cos of bt is the same thing. We work out to the same. And then now, instead of the with the sign here now, I'm going to take out the minus sign and put it out here. So that's so this minus is going to go. So I'm going to get minus a2 j sin bt. Getting to the point. So this is a1 plus a2 cos. We're putting these two together, the two cosine them together. So that's a1 plus a2 cos bt plus A1 J minus A2 J sine BT. Now, adding two constants together, we just can write down as another constant. So we're going to call this A1 plus A2. Let's call it something M. So A1 plus A2 equal M. We don't care what M is. And A2 plus A1J plus A2J is another constant, N.
You mean minus, right?
Huh? Yeah, A2, A1J minus A2J. We're just calling another number. We don't care what it is. So, all right. So the whole idea of the whole entire thing now is that I'm saying is that if you have a complex number, then as your solution to your K, then A is the real part. So the solution is e to the real part t, whatever the constant you choose, m cos the imaginary part, b is the imaginary part, cos plus n sine bt. So you were probably told to just, when you get a complex number, so let's go over here, go back over here. So this is our solution for our auxiliary equation. So what I'm saying that we can do, when we get the solution to the auxiliary equation, what we are going to write is that I, and I'm going to write it as a function of time, is going to be equal to the real part, e to the minus, the real part, e to the minus 250. This is the real part. Bracket m cos root 21 over 5 t plus n sine root 21 over 5 t, the imaginary part. So that is our solution. And it makes sense from an electrical point of view in this particular problem, because if, let me draw it up here. Pretend that that's a straight line. Our exponential part, e to the minus 250, will be like and our oscillatory part. Let me try again. Not much improvement. So this is how our current will vary with time. So what we're saying is that when you close the switch, current is going to flow in the circuit, but it's going to oscillate and it's going to die away eventually. All right. So we have that kind of relationship there. So the solution tells us what is going to happen to the current as it flows in the circuit. And so we can find the voltage across the resistance and find the voltage across the capacitance and all those type of things. Because since we know the current, then we just have to integrate the current to find the voltage across the capacitance, differentiate the current to find the voltage across the inductance, and multiply by the resistance to find the voltage across the resistance, as long as we have I. Because remember we had said that the voltage is I times R for a resistor, I times L times di dt, L, the inductance times the derivative of the current. So we just have to differentiate this and integrate it. Although it wouldn't be me integrating it, but integrate it to find the what is the current, the voltage across the capacitor at any different moment in time. So all that is just saying is, all I'm trying to get at is that the differential equation, we have model systems and understand what is going on using our differential equation. But it's just that we have to know how to handle and solve it. So suppose now we had a force in voltage. We had a source in the system. What would we do? So I want to just end this evening by looking at suppose my input is 5. And that says suppose my input is not 0, it's not homogeneous. Suppose my input is 5 volts. Then what is the process? What do I do?
So we would use one of the other processes. But I was trying to remember. I remember like one of the sort of problems was using, I think it was called Bernoulli's principle, I think. But you have I think 4 complete methods. Sorry, I was saying I believe that there were, when we learned it was 4 methods for different situations pertaining to a differential equation. I believe, if I remember correctly, I think one of them was Bernoulli's. Another one was when you, another one was like if you have an exponential function or something to that side. I'll have to look into my book to refresh.
Hello? You disappear. All right, so you have different situations because this here, it could be the same circuit, for example, and you had a sinusoidal input like sine t. Suppose you had that, then that would be 4 sine t. So the differential equation, the voltage would add up to 4 sine t. All right, so here's one method that we use to solve it. First of all, you have to solve the homogeneous equation. Same way. So that would be k squared plus 3k plus 2 equals 0. And it's me make up the problem, so therefore the solution there is y equal ae to the minus t plus called A1 plus A2 e to the minus 2t. So that is the solution to the homogeneous equation. But we do, this equation is not equal to 0. It's equal to 5. So one of the is two methods we're going to be talking about. And one of them is called one of them is using Laplace transform, and the other one is that we are going to say that if I differentiate and differentiate and differentiate and get 5, then that 5 must have come from something linear. In other words, I always say the baby, the 5, must look, the parent and the baby must look alike. So the 5 must come from something that we differentiate and differentiate and differentiate, add up everything, and we get 5, a constant term. So therefore, we're going to try y equal ax plus b, a linear function. So we know when we differentiate a linear function, we get a constant. So we're going to try a linear function. All right, so when we differentiate, try at. So dy by dt. When we differentiate this, what do we get?
A, sir.
A. Now we differentiate it again, what do we get?
0.
0. So we're going to plug that into our equation that we have up here. I'm going to put it across here. Is a complete that we write all over the board. 0 plus 3a. We put in the a for the dy dt. And then 2y is plus 2a t plus b is equal to 0. So this is going to be 3a plus, not equal to 0, it equals 5. Sorry about that. Because the equation is equal to 5. So it's equal to 5. That's 3a plus 2a t plus 2b is equal to 5. Now, immediately, there's no t over the right hand side of the equation. So immediately, 2a must be equal to 0. That implies that a equals 0. And so 3a plus 2b, the constant terms, must be equal to 5, which gives me that 2b must be equal to 5 since a equals 0. So b is equal to 5 over 2. As, like I tell you, the baby must look like the parent. So the y is going to be equal to 5 over 2. So for my trial solution, y is going to be equal to 0 t plus 5 over 2. So now my general solution for this differential equation. Remember now we solve the homogeneous equation, and then we say that this constant term, or as we have do it in engineering, we say that this DC component that we are going to have is that y is going to be equal to a1 e to the minus t plus a2 e to the minus 2t plus the DC component, which is 5 over 2. So let me just write down that. And what that DC component is an offset, meaning to say that when I draw my equation, so this is my line, this is my next line, I'm going to have to draw another line at 5 over 2. and that becomes my new axis. So my curve is going to look something like this.
Sir, just a question before we move forward. We assume that we said that A is equal to 2A is equal to 0. Is it because time is 0? So we just times it by 0?
No. We are saying that over this side of the equation here, there's no t. If there was a t, suppose I had in, I make it smaller. Oh, okay. Suppose this differential equation here had 5t, meaning that the voltage was growing with time. Then now I would have a 5t here. And then I would compare the two sides, and this would be 5t, and then I would say 2a equal 5, and so forth and so on. All right. The thing about when I keep on saying the baby must look like the parent, I already knew when you do the method of this is called the method of undetermined coefficient. I already knew that if I have a constant, so if I already knew that if I have a constant here, this constant input here, then my output is also going to be the y value is going to be a constant. So I should have really started with just y equals some constant, which I'm going to call p, and work it out from there. But I was again trying for the most general solution that we can have. So usually, whenever you look at the whatever the value of the constant term in the differential equation is, usually start one step up. So for example, if I had 5t squared, then I would try something with 5t cubed, at cubed plus bt squared plus ct plus d. I always start one step up from where the equation is, just to make sure. But in general, it's always redundant.
Okay, sir.
So you can answer your question.
Yes, sir. Well, that's fine.
The only reason why I put this as 0 is because there's no t over this side. If there's a t over there, then it wouldn't be 0. Comparing coefficients. So this side must be equal to 5. It will have no time component in it. So therefore, this has to go. So that has to be 0. Answer the question, or is still
Yes, sir. I'm clear.
All right. All right. So so the general point that I'm making is that we use differential equations to model all different kind of systems. And then when we model the system with the differential equation, then we have to turn around and solve that to find out if it's an electrical circuit, then what happened to the voltage across each of the components? Does it exceed a certain value that we can go over, or does it not? What happens to the current in the system? What happens to how are these various components related? We can, once we form an equation for the system, is then the problem is to solve it, and then when we solve it, then we can determine all the parameters of the system that we need to find out and work out what needs to be, work out the voltages and the currents or forces or whatever it is that we are modeling. But once we solve it, once we form the differential equation, then we have to then proceed to attempt to solve it. All right. So that is why we need to look at all various types of differential equations. So, like I said, I usually just start by going through 1 and 2 fundamental things, and then as time goes by, we will proceed. I'm not going to say anything more this evening. I don't know if anybody else is supposed to join the class. You will see on, when is it, Thursday or Wednesday, we have a tutorial session. For now, we're just going to be lecturing until we have enough content that we can run a tutorial session. All right.
So basically, until we have the contents, no Thursday class.
Or is it that you want to use the tutorial class as a lecture, sir?
You will pick.
Sir, can you scroll up?
You can run the lecture and a tutorial.
Yes,
All
sir.
right, cool. We finish quicker. All right, so we continue with this discussion on Thursday. And I will send the various things, the links and the support in the group. So,
Sure.
everybody have a link to MATLAB, right?
No, sir.
No, sir.
No, sir.